Good day to you. I hope you're doing well. This is the video for A8, which is special right triangles on the unit circle. The end output of this assignment is a unit circle with the special right triangle angles labeled on the unit circle with their coordinate pairs, their coordinate points. So first off, just to remind you from geometry, similarity, these are all angle similarity. They share an angle here. They have a 90-degree angle, so therefore the remaining angle is the same. So since they are what we call similar triangles, their side lengths are proportional. That is, side length x is to side length y as side length A is to B. Right? And that's nice. So when we talk about special right triangles, 45, 45, 90, no matter how big this triangle is, its side lengths are going to be proportional. So first off, the 45, 45, 45, the 45, 45, 90 triangle. We remember from the isosceles triangle base angle theorem that if a triangle has congruent angles, then the sides opposite those angles are congruent. So whatever this side length is, it is the same here. So we use Pythagorean theorem and we have x squared plus x squared is equal to 1 squared, which means that 2x squared is equal to 1, which means x squared is equal to 1/2, which means that x is equal to the square root of 1/2. Now we have to remember that this is a square root of quotients, which is the same as a quotient of square roots, so we can write as the square root of 1 over the square root of 2, but then we rationalize the denominator by multiplying by 1, and we get square root of 2 over 2. Right? So all that just to tell us that if we have an isosceles triangle with a hypotenuse of 1, then its sides will be square root of 2 over 2 units long. This is good because we are on the unit circle. So there is the 45, 45, 90. Moving on to the 30, 60, 90. This one, we'll do a little clever trick here and make it an equilateral triangle. We're going to reflect a copy of it. Mine's perfectly reflected, as you can see. They're exactly the same size. I'm going to draw it a little better, just because I can. You guys know that drawing is not my strong suit. So here we go. We have a equilateral triangle now, and so therefore all the side lengths is 1. These are congruent. This is a perpendicular bisector, so 1/2. And now all that remains is to find this long side adjacent to the 30 degrees. And once again, we invoke our friend Pythagoras, and x squared plus 1/2 squared is equal to 1. And that means that x squared is equal to 1 minus 1/2 squared, which is 3/4. And then x is equal to the square root of 3 over 2 when we take the square root. So I'm going to erase this then. And the upshot is if we have a 30, 60, 90 triangle with a hypotenuse of 1, the side opposite the 30 degrees will be 1/2, and the side opposite will be square root of 3 over 2 units long. You may remember these from geometry. In geometry, every one of these is scaled by a 2 to make things easy for you usually. I try to not do that, but I don't, who knows what we do with you guys. That was a long time ago. Okay, so we'll move the camera over a little bit and move to the unit circle. So this is how I want you to use this information. We're going to go to the unit circle and say we turn an angle of 135 degrees. Okay, well, if we do that, what kind of angle, what kind of triangle do we have here? Oh, it's a 45, 45, 90. And our hypotenuse is 1, so we know that this side is square root of 2 over 2 length, and so is this one. And the coordinates there then are going to be minus square roots of 2 over 2, positive square roots of 2 over 2, because that's its coordinates, right? So you use the special right triangles to place those coordinates. Remember on the unit circle that the x coordinate is the cosine of an angle theta, and the y coordinate is the sine of an angle theta. So the sine of 135 degrees is square root of 2 over 2. The cosine of 135 degrees is minus square roots of 2 over 2. You can compare these numbers to what you found yesterday when I asked you in A7, or the other day when I asked you in A7 to just do this with your GeoGebra manipulator. Okay, here's another one, 210 degrees. Remember that we're always measuring counterclockwise from the x-axis. If we are at 210 degrees and we've turned 30 degrees farther than 180, and so we have a 30, 60, 90 triangle, something like that, and then we go look at our triangle and say, okay, what's happening there to get to this point? This side is 1/2, and this side is square roots of 3 over 2. So the coordinates here are minus square roots of 3 over 2 and positive 1/2. So therefore the sine of 210 degrees, 1/2. No, minus 1/2, isn't it? These are both negative. The sine of 210 degrees is minus 1/2, and the cosine of 210 degrees is minus square roots of 3 over 2. The tangent. Remember, tangent is y over x, so you would take this and divide it by that. That would give you 1 over 2 square roots of 3, which would be square root of 3 over 6, I think. Anywho, that's what you're doing for the next assignment. And you want to do this for all the multiples of 30 and 60 and 45 that are, well, 30 and 45 I guess I could say, that are all on your unit circle. So you want to make a sketch of the unit circle, put all these angles on there, use this special right triangular relationship to fill in the unit circle. If it's helpful, you can make little triangles. Remember we had special right triangles when we sang the campfire song? You remember, I know you do. So get this unit circle populated with all the coordinates using the special right triangles, and take a picture of it and give it to me. I love you, peace out. Email me if you need things. I gotta stop saying that peace out thing. Kick one off for the VIP crew. How's that?